Okay, good morning everybody. और कभी कभी तुम लोग भी कह दिया करो गुड मॉर्निंग.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
तो YouTube पे लाइव हैं हम. YouTube पे फुल रेजोल्यूशन आता है, दिखाई देता है मेरे सर से बाल कितने कम हो रहे हैं. Anyways, सच्चाई छुपे नहीं छुपती. क्या कर रहा हूँ. Okay. All right. So good morning everybody. Welcome to physics, quantum physics. Yesterday we were talking about 2D potential well, and so where is it? Yeah, yesterday was a short class, so we didn't really talk too much. But what I had basically explained to you yesterday was that how to write down the Laplacian in polar coordinates. That was pretty much it. So we get this Laplacian. Now the question is, what do we do after this? So how do we solve it? Let's see. Plus 48. Okay. So okay. Now, so we have an equation which is, we have a Schrodinger equation, right? Which is a multivariable partial differential equation. So how do you solve such equations? Well, if you are lucky, then you can use a method which is known as separation of variables. So what that means is you can write out the solution, whatever the solution is, as a product of functions of the individual variables. So actually my big theta looks too much like my little theta, so I'll make it something like this. So this is our Ansatz. This is German word. In physics, we have a lot of German words because German physicists have, done a lot of physics. So maybe when Indian physicists do an equal amount, we'll end up having some Indian words or Sanskrit words, but that day is not there yet. So we have this Schrodinger equation, which is basically minus h bar square 2n del square plus v xy sin x. Okay. Now, so what happens when I make this assumption and insert it into this Schrodinger equation? So let's see what happens with, for instance, this del square, and of course I should be writing r theta, r comma theta. Okay. So if I do this, Then let's see, I have dr square plus 1 by r square d theta squared r times r, right? So now when you take these partial derivatives, what will happen is that in the first term there is only there are no mixed partial derivatives, right? That is the thing. So there is no term like dr d theta. So the first term will we can write as theta this times r double prime, right? And this is the second derivative. Okay, so when you put 1 prime, that's the first derivative, second derivative. So, yes, the next term is 1 by r square, and then this is just r, and then this second derivative. Okay, so now the next thing is that you take the whole equation and you divide it by psi. Okay, so in the kinetic term, what will happen is you divide the kinetic term by psi, and all the other terms also. We'll see what happens. So when you divide this by psi, right, what you're doing is you're taking this whole thing and you're dividing by r times this theta, right? So what happens in the first term? The theta function will cancel out. You will be left with r double prime r. In the second term, the r factor will cancel out. You will be left with this times this theta by r square. Okay. So we put all this back into the Schrodinger equation. We get h square by 2m r double prime r.
Sir, in denominator, that term will also come now in below r double prime r and rr.
Thank you so much. Right, that term will be there. Okay, and we will set v is equal to 0 for the time being. And on the right side, what will happen? We'll get e times psi, but then we are dividing by psi, right? So it's just e. Okay.
What do?
Huh? So is this fine? So after this derivative, after this Laplacian acts on psi, you get this. Then we are dividing by psi. Okay. We are dividing the whole thing, both left and right hand sides, by psi. So now, what is the resulting expression? Let's see. I'll put this minus 2m and so on the right side, and I will write it as k square. Right? You all know now that 2m by h bar square can be written as k square. So on the left I have, and I'll just understood what these quantities are. This is equal to minus 2m e by h bar square, which is equal to minus k square. Minus k square here. Okay. Now you take the whole thing, whole equation, and multiply by r square. What do you get? You get r square prime r plus this is equal to minus r square k square. You can write this as r square double prime r plus r square k square plus this by this is equal to 0. Okay. So now what have we done? We have reduced our equation to a sum of two parts. One part is entirely a function of the one coordinate r. The other is entirely a function of the second coordinate theta. And what is the statement? That the first function r of r plus the second function of theta is equal to 0, right? And the thing is that this is an identity, because we have not made any assumptions about what the values of r and theta are, right? So there might be some special values, for which there is some singularity, there is some singular solution. But apart from those singular points, this is true for all r theta, right? Okay. So that is only possible if these two individually are equal to 0. Oh, sorry, no. That's not 0, but individually, this is a constant. So I will write this as, let's say, m squared, and then f2 theta is equal to minus m squared. So whatever f1 r is, it has to be equal to minus f2 theta, right? And so that is basically the point of doing this. And I'm choosing this. I'm writing this as m squared. I can write it as some constant a and minus a, or I can write minus a and a. But then later on, when I solve the problem, I will see that I will have to come back to this. So that's why I'm sort of like choosing this, because I know kind of beforehand what the solution should look like. I think some people are having network problems. So if you have some difficulties, you please use YouTube. I will send you the notes for today's class and yesterday's class also. Nobody is on YouTube right now. Okay. So is this fine? Is this clear why this should be the case? Right? I just don't want to throw it to you as an assumption that you have to take for granted. You please understand why this should be the case. Okay. So now, once we have this, then the problem separates into two different equations. The first equation is the r part is equal to m square. And the second part is this is equal to minus m. Right? Now we can immediately solve both of them. The angle one is more easy, axial one is more easy, because this is what? This is right. This is just the harmonic oscillator. So what this tells you is that when you look at the wave function, right? So now the wave function has circular symmetry, right? And when you look at the wave function, as you go around in a circle, right? So as you go around theta, right? So what do you get? You get standing waves. Now you have to get standing waves. Right? You have to get standing waves. So the equation has to satisfy continuity, right? Because when you go around one full circle, so psi of r theta has to equal psi of r theta plus 2 pi, right? So that means okay, and this means that this expression, right? This theta. So we'll see what consequence this has, right? But the obvious consequence is that what will happen is that m will be a multiple of so m will be an integer, and it will be an integer multiple of n, right? No, it will be some integer divided by 2 pi. So then what will happen is that wait, this 2 pi hota hai. It will just be an integer. What am I saying? It will just be an integer. Is that? So if m is an integer, then this will be a periodic function in 2 pi, right? E to the I 2 pi, e to the I 4 pi, so on. Okay. Now let's look at this. Right? Okay. So now this one looks a little bit more complicated, but let's see what sort of, again, we should try to use some sort of symmetry argument. Okay. So one possibility is that what sort of solution you can have is that in the radial direction. So if I look in the radial direction, so now this is r and this is the amplitude of the wave function, right? So it's the same in all directions, no? Because there is no dependence on theta. So what should be the form of this? Well, you know, for the ground state, it is safe to assume, so if you have some sort of finite potential, it is safe to assume that the ground state might look like this. Something of this form, right? And so we'll try different solutions. Let's say we say r is equal to e to the minus r square by L square. So what will happen? So this will not solve this. This will not solve the solution. So we will get this. I think this is one of those special functions. You will get I think Jacobi polynomials or something like that. So I have to look that up myself. Okay. So I'll leave that for later. So we have the solutions all worked out. All right. We'll come back to this problem and once I remind myself what the solutions are. Okay, but this is the general procedure. So you apply the same kind of thing, for example, when you are in 3 dimensions. So in 3 dimensions, for instance, what do you say? You have r, theta, phi. Now you have 3 angles. These are polar coordinates. I hope everybody knows what the 3-dimensional polar coordinates are. If you don't know, please tell me. Everybody knows?
Yes, sir.
Okay.
Yes,
Manoj
sir.
Babu, you know what spherical coordinates are?
Hello, sir. I'm audible.
Huh?
Yes, sir.
Aapko, you know, and Jatin?
Yes, sir.
That didn't sound like a very confident yes. Let me just quickly tell you. So spherical coordinates are, r is just the radial parameter. R as usual is just x square plus y square plus z square. This theta is called the, well, one is called polar and one is called azimuthal. I always forget which one is which one. So basically, if you have some point, some vector, you have some arbitrary vector. So this is x, y, z. So this is some vector r. And now you can project it down to the xy plane, right? So the coordinates of this are x, y, and z. So you project it down to the xy plane. What that means is you consider this coordinate has, this point has coordinate x, y, 0, right? And then you look at it will intersect the x-axis at some point over here, right? And then this will intersect the y-axis somewhere over here, right? Now, theta is this angle. So it's the angle the vector makes from the z-axis. And phi is this angle. Phi is the angle the vector makes with respect to rotations around the z-axis. So you will get x will become, for instance, so this is theta, so x will become r sine theta cosine phi. Y will become r sine theta sine phi, and z will become r cosine theta. Right? So this is your spherical coordinate. So again, in spherical coordinates, we would repeat the same procedure. We would write down the Laplacian in terms of r theta phi. Of course, you would do so only if the problem requires you to do so, right? So if in the case that, let's say, your potential you have a spherically symmetric potential. So what is an example of a spherically symmetric potential? V x y z or V r theta phi. Well, a spherically symmetric potential is one which doesn't depend on theta and phi. So it's equal to some function of r alone. What sort of potential has that property? Well, any function of r is a spherically symmetric potential. But a few in particular are important. One, for example, is this one. What is this? This is a Coulomb potential, -1 by r. Then you can also have something like this, 1/2 kr square. So this is like a harmonic oscillator in the radial direction. It's like a spring attached with one end attached to the origin, and you can pull it and let it go. So it, it goes back, but then it also has a freedom of motion in theta and phi. So again, you would proceed with the same way. You would say that you assume that you can write down, you can express the state as a product state, right? Separation of variables. And then you insert this into the Schrodinger equation. Right? You divide by psi, and then you get 3 separate equations. For r, the function r, the function of theta, and the function of phi. And then you open some mathematical physics book like Ask and Weber or whatever, and generally R will be the one which will have some complicated equation, and you see what sort of differential equation is, and you solve it. Okay. Now the thing is, see, in general, I mean, it's for most of us, I think it's not really feasible to remember all the different kinds of differential equations and all the possible special functions. So that's why I'm telling you the general procedure, right? So even I don't remember, like, so I will have to go and look this up. But the point is that it's like doing chemistry, for example. You can't remember the combinations of every single chemical, right? So that's why you have some big thick handbook. And so you look up chemical structure in that handbook. Okay, this is what it is. It's the same thing, right? You look up the mathematical structure in some handbook. Okay, so now I think we have talked enough about the 2D potential well. So we will come back to this problem of 2D and 3D. Okay, so we'll have a full week dedicated to the special functions and all that. But in the meantime, let me introduce this concept of density of states, which arises when you are in 2 dimensions or in 3 dimensions. Okay, so Dheeraj was watching. He put his name and then he left, I think. Okay, anyway, or maybe Dheeraj has joined us on Zoom. Well, Dheeraj Gupta is on Zoom. So what do you mean by density of states? Okay, so let us look at, we have the solution of this harmonic oscillator, not harmonic oscillator, sorry, 2D potential well, right? And in the 2D potential well, right, we find that assuming, so for simplicity, I will take both sides to be of equal length. That's why I'm calling this psi and psi. This is the same function. If you have unequal length, then you can put psi of x and psi of y, but just it's not going to change anything, right? And psi of mx is root of 2 by L sine m pi x pi, right? Same thing for that's what this psi is. Okay. Now we can ask what are the energies of these states? Okay. So what will be the energy? The energy is so we are looking in the potential well. Inside the potential V is 0, outside is infinity. So So what is the energy going to be? The energy is just going to be minus h square by 2m del square psi, right? So E times psi, this is an eigenvalue equation. Now, what does this give us? The del square, remember, is just dou x square plus dou y square, right? So if you do that, dou x square plus dou y square, what do you get? You get h bar square by 2m. And okay, so this is the mass. So let me use a different m for this because I don't want you to confuse this m with this m. This m is an index and this m is the mass, right? So when you take this the second derivative, you will get m square pi square by L square, right? And basically the energy will end up being equal to h bar square kx square, right? Times psi m plus h bar square ky square. So this will be psi m psi n y like this. And what is kx? Kx is equal to m pi by L and ky is equal to n pi by L. So is this clear? Am I going too fast? Please tell me, because if I am, I can slow down and go over these things again. So if you look in the participants window, can you open the participants window in Zoom?
Yes, sir.
Okay. Do you see at the bottom of that window there are some buttons? Yes, no, go slower, go faster. Do you see those buttons?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So I want you all to press either go slower or go faster, depending on whether you think I'm going slower or faster. Can you all do that? Somebody has given thumbs up. Thumbs up is also okay, I guess. That means neutral. I take thumbs up as neutral. Okay. So far, nobody has said go slower. So I take it that my pace is okay. Maybe I'm a little bit too slow. Now, what this tells you, so if you put this in, what do you get? You find out the energy is a function of these two numbers, m and n. And what is it? H bar square pi square by L square. And there should be a factor of 2m. I forgot the factor of 2m. That's right. 1 by 2m mass has to be. So h bar square pi square by L square, then 2m L square times m square plus n square. So these are the energy eigenvalues. Okay, now let us look at this let us make a plot of this in this plane, mn plane. Okay, so m and n, they are both integers, right? So m is equal to 1, 2, 3, 1, 2. So first of all, what will be the lowest energy? The lowest energy will be this 1, 1. Right? And 1 will be h bar square pi over capital M L square. I just want to make sure I have not made any mistakes as far as maybe this factor of 2 you should please check, okay? If I'm missing it, if I'm making a mistake, I'll leave that for you to check. Then what about the next highest state? Well, now the next possible values of M and N. Now there are two possibilities. You can have E12, but you can also have E21, right? So you have E12 and E21. And now the thing is that both of these are different states. These are not the same state, right? But they have the same energy. So that energy is it's pi square. So 4 plus 1 will be 5 by 2 capital M L square, right? Then the next state will be E22. E22 again, there's only one state. So let's say that we make a table of the energy eigenvalues. So what is the energy? The first energy is so we'll say the first energy eigenvalue, we'll put it like this: E1 is for E11, then E2 as for E12 and E21, then E3, well, that's just E22, right? Then E4. So by E4 I mean the fourth highest or the third excited state. Okay. So this will be E31, E1, and so on. Now, so what do we have, right? So as you go to higher states, what will happen is eventually you will start to have more and more states with the same energy, right? Basically, you have to have a solution of this this equation that m square plus n square has to equal p, where p is some positive integer, right? So when p becomes large, like p becomes 15, 20 or something, what will start to happen is that you will have more and more possible combinations of m and n, such that m square plus n square will give you p, right? So here, so this is the energy, these are the possible states. So this is degeneracy. So degeneracy means that you have states which have the same eigenvalue. They are different states, but they have the same eigenvalue. So here the degeneracy for the first one is 1, then 2, then 1 and 2, and so on. Okay. So now what one can do is you can make a plot of this degeneracy. Okay. So this degeneracy I'll call n of e. Let's see what is n of e as a function of e, right? Taking a guess that, well, it will increase the monotonically increasing function, right? It will have some like some plateaus of or something like this, right? but it will overall be an increasing function. So this n of E, this is known as the density of states. Well, the density of states is actually dn by dE. So that means that when you look at some finite interval, let's say E naught and E naught plus delta E, right? Of these energies, then in that finite interval, you have some number of states, delta n, right? And that delta n will depend on your E naught, right? So this is a very important point, because what this tells you, for instance, is that as you go to higher energies, for the same energy, the population of states has increased. Okay. See, you don't have this, for example, for the harmonic oscillator in one dimension. In one dimension, in the harmonic oscillator, all the states are equally spaced. So if you say that you want to write down a density of states, what do you get? You just get a straight line. You just get a constant. But you can look at the potential well, infinite potential well in 1D also, right? There also, the energy spacing is not equal, right? But it's a discrete set. But if you have to write down the density of states in 1D for a potential well, what do you get? You get something that will drop, right? The number of states per discrete energy level will drop. You won't get a continuous line, but it will be a decreasing function of E. Because as you go to higher and higher energies, the gap between the next energy and the first energy becomes larger and larger, right? Now, this density of states basically is a very, very important parameter. It characterizes the it determines the thermal, the electrical, and also in to some extent mechanical, properties of a system. So the system, for example, is a material. Okay, if you consider some material like you have some sort of lattice. Let's say you have NaCl, right? What is that? Salt, right? Common salt. So you have some two-dimensional lattice or three-dimensional lattice of atoms, right? And you can treat, so you will have, let's say, sodium atoms at the lattice, something like this. And maybe you can put chlorine atoms. Actually, chlorine atoms are bigger than the sodium atoms. So, but anyways, who cares, right? We're not doing chemistry, we're doing physics, something like this. Let's say you have this kind of thing. Okay, I'm not saying this is the structure of salt. You should look at if somebody goes and checks that. Okay, I'm just drawing some sort of lattice. So each atom has coordination number 1, right? 1 atom for 1 atom. So what will happen is that if you have if you have an electron, let's say, if you have an electron in this system, what will this electron see? This electron will see a periodic potential, right? it will see a periodic potential due to the presence of these ions. So if you look in one dimension, for instance, again for simplicity, then in one dimension the potential the electron might see could look something like this. Okay, so this is I is equal to 1, 2, 3, 4. So these are the lattice size. So you can make an approximation, right? That these are all finite square well. But the point is that you have some sort of periodic potential. Now, when you solve the Schrodinger equation in a periodic potential, so this is just, there's no need for that. When you solve for the density of states, when you solve for the Schrodinger equation in the periodic potential, again, what you will find is that, for example, your energy spectrum E of K, right? What is K? K is the wave number, right? It tells you the momentum of your particle, your electron. And you have an electron that is moving around somewhere in this potential. So this will be some function of K, right? Or you can just write it as some function of E also. So yeah, some function of K. And so then you can write N of E, right? This will be some function, some non-trivial function, right? And this density of states will determine, so you can have different possibilities. You can have a density of states. You can have a constant density of states. You can have a linearly increasing density of states, or you can have a density of states like this, or you can have something which goes down. These are all different possibilities, right? Now, what happens is that you imagine that, for example, you're calculating something like conductivity, right? So what does the conductivity have to do with this density of states? So you might remember that, there is the band theory of solids, right? So this density of states, right, will basically give you the band structure. So in a real material, the density of states will look much more complicated. But so this band structure allows you to determine, for example, whether a substance is going to be a insulator, a metal, or a semiconductor, right? And again, so for instance, if you have a lot of empty states, then that tells you the material can be a good conductor, right? And if you don't have any accessible states, if there is a break in the density of states, right, it's possible that the density of states can also oscillate. It can also behave like this. Let's say this is my density of states for some substance. What does this tell me? This tells me that if I have particles, if I have this is in this energy range, my substance will be a conductor, right? And in this energy range, where the density of states become very low, here I will have an insulating state, right? Because there aren't enough empty states for for electrons to occupy to be able to transfer energy through the material. So for example, this would be insulating, and this would be conducting. Okay, so this is one of the first places where you run into this concept, is in one of the simplest cases is in the 2D potential one. All right, so I think I'll stop here for today. And we will come back to solutions of equations of this sort when in one of the following classes. Okay. Questions? So for all of you who, when I was talking about coherent states, there were many people who weren't so thought that, well, coherent states, what is the theoretical use of all? What is the? I'll just have a drink of water. What is the practical use of this coherent state thing? So that is actually very, very useful in lasers and optics.
Lasers.
Right. But this is even more general, right? This applies to almost any material you can think of. These ideas of density of states and so on. Okay. So I guess I don't know. I suppose there are no questions. So okay, I'll just leave it here. We will. One of the things that we haven't talked about is a finite potential value. So that is a problem that we have to talk about. We'll be talking about the 1D finite potential value. But tomorrow, what should I do? What should I cover next? Maybe I'll do that. Maybe I'll do the special function solution. Okay. All right then. I'll stop the YouTube now.